Okay, welcome back. So, grain boundary strengthening. Okay, so, grain boundaries are very effective obstacles to dislocation motion. Right? They're stronger than dislocations or point defects like solute atoms. And so, imagine you're a dislocation on a slip plane. Right? Basically, you're going along and you're seeing a regular array of atoms for the most part. And then all of a sudden you come across a grain boundary, right? And the structure of the grain boundary is a mess, right? Unless it's a very special type of grain boundary, like a twin or a CSL boundary. For the most part, it's a total mess, right? There's no clear way to describe the structure of that boundary or how easy or hard it is to, or what it really means for a dislocation to transmit through a grain boundary. Right? Remember, dislocation is a line defect in a crystal. A grain boundary is a surface defect in a crystal. So what does it mean for a line defect to intersect that surface defect? What does it look like when it passes through? Right, these are all really open areas of research right now. So it's not clear, it's not clean. But for the most part, grain boundaries are very effective obstacles to dislocations, right? And the simple picture, the classic picture, is don't think about the dislocations going through, but think of them piling up at the grain boundary. And one dislocation hits the grain boundary, then another one's going to come, and it's going to interact with that first. And another comes up, and you get a stress concentration of these dislocations piling up. Right, and remember, right, here's our grain boundary, here's our schematic of these edge dislocations piling up. And they repel from each other. They exert a force on each other. So this dislocation is exerting a force on this grain boundary. This second dislocation exerts a force here, which increases the force on the grain boundary. The more dislocations we add up, the greater the stress concentration at this grain boundary. Right? You can imagine this now triggering a stress concentration, triggering slip in this other grain, activating dislocations over here, activating a dislocation source over here, right? Imagine you have a Frank Reed source or something. Now all of a sudden that can become active. So the general picture is at first we get this micro yield, right? We have a small handful of grains with slip systems that are favorably aligned in a polycrystal. Dislocations then pile up at the boundaries and can then trigger other local slip here. And then macro yield occurs when dislocation motion or sources are activated in a large number of grains. Right? So you have plenty of operational sources over there. So let's look at this a little bit more carefully. Okay, so imagine we're here. All right, this grain 1 has already yielded. Grain 2 has not. Grain 1 is more favorably oriented. It sees a stress state that is more favorably oriented to cause dislocation motion than the stress that grain 2 sees right now. And imagine there's some dislocation source inside grain 2 that is not yet operational, and it's some distance r from the boundary. Right? The stress concentration due to the pileup in the active grain is going to increase with the number of dislocations that come up against the grain boundary, right? And the number of dislocations that are available to pile up depends on the size, right? That makes sense. The bigger the grain, the more dislocations. All right. And so we said here tau star is the stress required to activate dislocation motion in the other grain. So it's going to be the applied stress minus the yield stress. And then here, this d by 4r to the square root. This is the stress concentration from the Hall patch, right? So this is the applied stress. This is the inherent yield stress, right? So this is what needs to be overcome to make flow happen. And we can rearrange this to give us the Hall-Petch type relationship. Right? This is the Hall-Petch coefficient, d to the 1 over the square root of the grain size. In class, we'll go through a little more physical derivation of the Hall-Petch relationship. Okay, so I'll have to do some editing there. I made a big mess of this slide, so I apologize for the jump cut. This is something I'm going to have to go over a little deeper in class. When I was explaining this through, I realized I made this slide a little sparse. So we'll work this out in more detail in class, and it's explained a little better in the reading. But remember what the Hall-Petch actually tells us, right, is how much more difficult grain boundaries make slip, right? In a very large grain, dislocations don't feel the effects of the grain boundary, right? Imagine if you have a single crystal, right? An infinitely large grain, those dislocations don't see the effect. But as the grains get smaller, grain boundaries are very effective obstacles to dislocation motion. So the Hall-Petch equation relationship quantifies, well, in a way quantifies, how effective grain boundaries are in providing obstacles to dislocation flow. Now remember, right, not all materials have the same Hall-Petch slope, right? Some materials, the grains are much less sensitive to the grain size than other materials. And also, we can see that this Hall-Petch slope depends on the pile-up behavior, right? So it's not too hard to imagine that it's also going to depend on the strain, right? Because the more strain you have, the more dislocations, the bigger this pile-up is, right? And if I can get enough dislocations here fast enough, then I can break through. Okay. So I'm going to basically skip to the main result right now, right? That this Ky is a measure of how fast the yield strength changes with more grain boundary surface, right? The grain size. The more strain you have, it adds to that effect. Okay, that's the main point. I'll talk about geometrically necessary dislocation density. I'll have to put together some additional content, I see. Okay, so this picture of a nice clean pileup is nice in theory, but there's not a lot of direct microscopy evidence for it. Right? We do see pileups, right? Don't get me wrong, pileups are a real thing, but the picture of a pileup and a Frank Reed source on the other side, that's not what we see. Right? The truth is, grain boundaries are really complicated structures. They act as some grain boundaries are really good at acting as sinks for dislocations. They'll just suck dislocations up, right? The dislocation will run right into the grain boundary with no resistance and boop, out of existence. Other grain boundaries are basically impenetrable walls and dislocation just bounces right off. Other dislocations, other grain boundaries can act as sources, right? And they can emit dislocations into the other grain. And the rate at which they will emit dislocations into other grains is going to can be strongly dependent on the stress that is there. So we can model this in a very empirical way, right, by introducing this parameter mu, which characterizes the ability of a grain boundary to emit dislocations, right? And we can think of mu being the total length of dislocations that are emitted from a unit area of the grain boundary. Right? And so we have a relationship between the dislocation density at yield, right, the number of dislocations. Right, this is the grain size, right, and so we can create a pseudo Hall-Petch relationship like this, right? But this is really just a very hand-waving argument at best. The real truth is that it's just a complicated mess, right? And so we can look at the Hall-Petch for different metals, and we see some trends, right? HCP metals with a limited number of slip systems have high Hall-Petch coefficients, right? High Hall-Petch coefficients can further be correlated with inherent strength or to higher elastic moduli, right? That makes sense. The degree of grain size hardening depends on the Hall-Petch coefficient, right? And the degree to which grain size can be refined in the material, right? Well, obviously, if we can't shrink our grain size as small enough, it doesn't really matter what Ky is, right? So to be a really appreciable, to strengthen a material to a significant degree, right, we have a Ky square root of the grain size, right? We need to get our grain size down pretty small, right? Square root of 1 over the grain size, I'm sorry. We need to get our grain size down pretty small, right? And so grain refinement by severe plastic deformation is one technique. Right, but then you also get significant work hardening when you do that as well. But that's it for grain boundary strengthening, right? Unfortunately, this is an area where there's not a whole lot known. It's a really active and interesting area of research. But it can all really be summed up as grain boundaries are obstacles to dislocations. And grain boundaries can act as places for dislocations to pile up during slip. That causes a stress concentration. Anytime you have a stress concentration, you can then activate slip in other grains. but the effect is really not straightforward at all. Okay, thanks for listening, and we'll pop back up with solid solution strengthening, a topic that's a little more straightforward.